Everyone, welcome to our poster in the topic of computer-aided refrigerant design according to the new developments. I am Nishakon Kupasert-Wong as a narrator in this presentation. The presentation is start with the introduction, then methods and tools for refrigerant selection and design. Next is the application example. Finally is conclusion. Let's enjoy our presentation. Refrigerant is the chemical compound that flows through the refrigeration unit that defined by thermodynamic diagram and need a reliable model to design refrigerant systems. A new GC models are developed based on small molecules and used to predict important properties, for example, boiling temperature, critical temperature, and critical pressure. Is methods and tools for refrigerant selection and design, which is divided into the three sections. First, the database and property models section. This will talk about the database, which is divided into three types as in this ontology. A new GC model has been developed using measured data for boiling temperature, critical temperature, and critical pressure, considering compounds with 1 to 7 carbon atoms using the expression similar to the MG method as in equation 1. Table 1 presents the distribution of percentage of error for C1 to C4 of estimated normal boiling point temperature compared with measured data from regression of parameters. The boiling temperature of each compound are calculated with the regret parameters and compared with measured data. 85% of C1 compound has less than 1% relative error. The model performance for critical temperature and critical pressure correlated as a function of boiling temperature and are shown in figure 1 in terms of plots of estimated property values versus measured property values together with R-squared statistics, which show very good model accuracy. Next is the method for refrigerant selection and design includes three steps, which are define target property or functions. Second, find candidates that match the targets. And finally, verify the selected candidate through process performance simulation. The target property has divided into two sets. Set 1 consists of boiling temperature, critical temperature, and critical pressure. This property influences the phase equilibrium for the pure compounds and mixture. Set 2 consists of properties such as heat of vaporization, GWP, ODP. These properties influence the performance sizing of the process. Make sure that all consistency rules are verified. The refrigerant selection has divided into two cases. Case 1 is the single compound. The set 1 property are matched as close as possible. Set 2 is mixture compound. The set 1 property are exactly matched by using the equation in table 2 to calculate mixture composition, and the set 2 property are matched within the specific bounds. Finally, the method for refrigerant cycle simulation. The operations for one refrigeration cycle are shown in figure 2 and a corresponding process model has been developed as presented in equation 6 to equation 8. Also, the performance of different refrigeration processes are compared in terms of COP presented in equation 9. Next, we will give three application examples. Example 1 is consistency of data, models, and CMD solution. The need for more accurate property models together with the need to use measured data for target properties in refrigerant selection. Examples of report feasible candidate molecules are given in Table 2 together with the target they are supposed to match as well as measure and estimated values. If single molecular replacements are being sought, deviation of more than 10 Kelvin from the target value may result in infeasible refrigeration cycle operation. However, As mixtures are being sold, then the target temperature can be matched exactly, but the mixture compositions would not be consistent. The consistency check is presented in Table 3. Then apply the refrigerant model by replace and evaluate R134A. Table 4 lists selected alternative refrigerant for R134A in terms of single, binary, and ternary mixture. From the Table 4, the boiling temperature of alternative single refrigerant is close to the target boiling temperature, but the boiling temperature of alternative mixture is exactly matched with the target boiling temperature. The compute COP of the alternatives is compared with R134A, which are done with the Pro REFD software presented in Figure 3. Similarly to the second example, this will replace and evaluate R12, which the result is given in Table 5. To be concluded, refrigerant design and selection together with refrigeration process performance can be performed reliably and efficiently through the CMD technique. A new class of GC models suitable for refrigerant molecules can be developed and validated with mature data. It should be noted that the scope and significance of methods like CMD depends on the application range of the property models. Thanks for your attention.